Hi everyone, welcome back. This is a continuation of our discussion from last week where we got a quick introduction to YOLO version 8, and we actually loaded an image and loaded a couple of pre-trained models, one for object detection, one for instance segmentation, to segment that specific image. And we saw that, okay, for object detection you get the bounding boxes, and for instance segmentation you get both the bounding box and the pixels, corresponding pixels actually segmented. Now in this video, let us take it to the next level, which is, okay, all that is great. You're segmenting objects in the kitchen, but I want to segment objects in my scientific image. I'm going to use a electron microscope image from a public data set. It does not matter. You can be using your remote sensing image, your aerial photography, or MRI. It doesn't matter. Anytime you have objects that need to be segmented, you just load a data set and train a model, segment, and then perform analysis. And that's exactly what the goal is for this tutorial. And again, I know you love this content, so please go ahead and hit the subscribe button right now. And also, if you're feeling extra generous, try to find the thanks button and contribute based on how amazing, awesome you're feeling that right now. Okay, let's look at the plan. Actually, in the last video, I provided a quick introduction to YOLO V8, so please go ahead and watch it. But again, a quick summary of that. YOLO version 8, obviously 8th version, that means there are previous versions in YOLO. This one is better, obviously, I hope, right? I mean, as every version goes by, because it's better, because it's faster, and it also adds certain new functionality, which is instance segmentation, for example, that makes it usable for scientific applications. Now, YOLO is a AI framework that supports different types of tasks. And what tasks, if you ask, it can support, it does detection, segmentation, classification, post detection, and so on. I am going to focus primarily on the instance segmentation, or the segmentation part of it, in this specific tutorial. The usage is very similar, whether you would like to do other, detection or tracking. And they have pretty good documentation, so please go ahead and look at their documentation for any of the other ones that I'm not covering here. Now, how do we train it using custom data? You need to get the data ready. And again, I have done a video number 332, not the last one, but the one before that. Please watch that. If you start with binary images and you want to convert that to YOLO compatible format, that video is for you. I shared a bunch of code, so you can take your images and do that. Or you can use some third-party services. So the plan for now is prepare the data, like I was just mentioning, by converting existing annotations to YOLO compatible format. This is exactly what I'm going to use today. But if you don't have that, you can just start with your raw images. Go ahead and paint them in RoboFlow and convert them into YOLO V8 format. Or if you already have Coco style format, maybe you have used makesense.ai to paint your pixels, and now you have a Coco JSON file. You can just drag that into RoboFlow and you can convert that into YOLO V8. In fact, I'll do a quick demonstration right before jumping into the code in doing that. And the next part is walking through the code in Google Colab. And what do? We train a model. This is, again, a complete project. You're starting with raw images, and this is a full project using YOLO. Very similar to the one I have done using Detectron a few videos ago, and go ahead and watch that if you haven't watched it. It was like a 50-minute video or something. I hope this doesn't go that long, but hopefully you'll find these long videos to be informative and not boring. I hope so. If you find it boring, let me know so I can optimize the way I record these videos. I'd rather not miss any details, than make the video like confusing and make it faster, right? So that's the balance I chose. Okay, so we are going to walk through where we are doing training, and then we are performing inference on new images, and then we'll extract area calculations and all that. Just very similar to what we have done with Detectron 2 video. Okay, now first let's understand the image and the data set in this specific case. and you can download this. And this data set is cellular segmentation of these organelles in 3D EM images. Like these are human platelets. And you can download the data. The link is down there. And by the way, when I shared this with Detectron 2, I got a lot of messages about, hey, the data set is not available. Can you do this? I'm like, what the, what? I mean, guys, it's not a data set I uploaded, right? It's not a data set I uploaded and put it on my Google Drive, and I don't own this. So what do you do if that doesn't work? You freaking Google search. You cannot be data scientist if you don't know how to hunt for your data. If it's not there, Google search, find this, follow. I gave enough information. By the way, I'm giving you a direct link to .zip file, but that may go away later on. But there may be some version of this data set somewhere floating around. If it's not there, I can't help you because this is not my data set. Please understand that. I legally cannot share data set that does not belong to me. You shouldn't either. The people who own the data set, they share it, we use it. And that's why I'm putting the reference right here. Sorry for my 1-minute rant, but the thing that I really don't like and I want people to learn is data curation, data hunting. You go hunt for the data. You should have that killer spirit. If you don't have the data, what can other person do? Go do a quick Google search and you get 20 links, and one of those links will give you the data. Sorry, I'll stop my rant, but some of you probably relate to that when people ask questions that can be answered using a quick Google search. But other technical questions, I'm not saying don't ask questions, but don't ask questions that could be easily answered by 1-second Google search. Okay, now let me get back. Calm down. Let me get back. And the description of the training data. So it's a bunch of images, as you can see. They're all noisy, so makes this a bit challenging. And let me just skip through this. What I am using here is, this doesn't, actually I should have deleted this slide. I'm not just using 5 images for training. I'm actually using a lot more images than 5 images because I initially started painting these and I got super lazy and I'm like, okay, this is not what I want to do. My skill lies in actually using coding to automate the task. So I have written code to convert my images into YOLO annotations. That's exactly the video I did in 332. So after doing that, so there's no way I'm gonna paint all these pixels because I already have annotations, right? From these guys. Okay, the 4 organelles that we are going to segment here are the cells, mitochondria, alpha granule, and carnicular vessel. So the what is that color? The orangish color, the big blobs, these are all the cells, and mitochondria is in red. We don't have a lot of mitochondria, so the accuracy on those would be very low. And alpha granule is these green blobs, and the carnicular vessels are the blue blobs right here. Okay, so these are the 4 classes that we are using for training, and with that information, I think we should go ahead and jump into the code without wasting any more time. But again, I would like to just show you this Leapman Lab webpage where I actually downloaded the data from. It says dense cellular segmentation for EM. Again, use that as a keyword and you'll probably find this page. But when you scroll down, it gives you a lot more information about this data set, more than I could share. And the data is down there. Go ahead and download it. It's only 180 megabytes, and they have training, validation, and testing. I'm only using the training and validation data sets. So I downloaded them and I used my code. In fact, do I have it here? I think, yeah. I used my code to convert those input training images, like these images, and training masks, like these binary masks, into a YOLO style format. So the YOLO dataset format is right here, where you have the training data, validation data. Within the training data, you have images and labels as text files, right? Right here. For each of these images, you have a corresponding text file. Okay, and And what else do I have? I have data.yaml, and the YAML file is nothing but it tells you how many classes you have, and what the class names are, and what the directory paths are for your train, validation, and test data sets. Now, if you don't know any of these and you just want to, you don't want to use my code. Let's say you have your input images, you already have them in Cocoa format, which means you have your input images and the JSON file right there, right? How can you generate your labels? You can go to roboflow.com, create a free account, and any free account, I believe, any data you upload is going to be a open source data. So usually if the data set doesn't belong to you, I get my stuff done and then delete it because I'm not the owner. That's exactly one of the reasons why I did not upload the entire data set to this public repository, because again, I do not own the data. So I'm going to process it offline, and I'm using it for training purposes, right? So for tutorial purposes. Okay, I can't stress enough on on the topic of respecting the licenses when it comes to data, when it comes to code, when it comes to anything that's not yours. When you touch it, you have to credit the right people. This is very important, especially to those who are just started to getting into your graduate school or undergraduate school, or doing your doctoral or postdoctoral. Okay, where am I? I seem to be very talkative today. So let's create a new project. Well, I have a project called Junk with nothing in there. So let me open my folder. I have trouble seeing here, and I can just drag this. Let me go back and drag the entire train folder right there. It understands the JSON file, and it looks at all your images. And as you can see, RoboFlow is pretty amazing. It actually automatically, it put everything right there. If you want to add more in addition to that, you can always add more. You can go to a class and you can use any of these. And by the way, it's also powered by Segment Anything model. So it assists in annotations if you are starting from scratch. Okay, enough about annotations, but once it's all done, let's say, do I have a project? Okay. Ignore that. Once it's all done, you can basically, I don't want to save and continue. Let me go ahead, and I think let's take this example. You can export the data set. There are two things you can do. One, download the zip. So you have everything down and you can upload it, or you can show download code, in which case it shows you the code to download and with your API key and everything, and you just plug it into the code. I have included that in the file that I'm going to share, so don't worry about it. Okay, there is a lot we talked about data and all that. So let's, I think now you understand what we have, right? So what we have is a data in a folder called YOLO, and you have train with images and labels, and you have valid with images and labels, and you have data.yaml file. And by the way, if you export it from RoboFlow, YAML file gets exported directly. If you use my code from 2 tutorials ago, from 332, I included this little bit about YAML. All set. Enough background stuff. Now let's get into the actual code. Let's connect the runtime, and I chose GPU, of course. I added all kinds of text, and I also added how you can download the dataset with a direct link and all that stuff, blah, blah, blah. And I should have done a good job because I typed so fast. And where was that? Oh, God, I saw JSON. I made a spelling mistake somewhere. There you go, JSON. So, okay. I should have been a bit better prepared, but yeah, that's all the text you have. And if you want to know more about YOLO models, like, you can go follow this link. Let's go ahead and install Ultralytics library that we did in the last video. Again, this is where we are using to invoke our YOLO library, our YOLO methods. Okay, so that's installed, and I'm going to import YOLO from Ultralytics, and of course Matplotlib and PIL for image handling and plotting. This is very similar to what we have done in the last video, so you should not be surprised with that. And again, in the last video, we loaded the model, but in this case, I'm doing this in 2 steps. One, from YOLO, I'm going to import this model, -seg, which means it's going to be instance segmentation.yaml. And on top of that, now, when you only do this, this is going to be the structure of the model with random weights. I want to fill that with pre-trained weights, and that's what this point is right there. And this is the transfer weights. So now at the end of this, I should have a model that has been pre-trained on some images, right? I mean, it's not on our images, so it doesn't matter. As long as it's pre-trained, it's trained enough on these data sets to understand, to detect the edges, to detect like different textures and all that. On top of that, I'm fine-tuning it to my specific data set. Okay, let's move on to fine-tuning part. And if you want, this is where you install the RoboFlow library if you are importing the data directly. And when you do that in Colab, you will get, at least in September 2023, when you run, install this RoboFlow and try to follow this process, you'll get an error about some sort of an encoding error. To bypass that, to handle that, let's go ahead and run these lines. Yeah. So import locale, and you're actually setting your locale to understand the UTF-8 encoding. Again, if you don't know what that means, it doesn't matter. Just go ahead and run this line, and then you can install your RoboFlow. And then, I don't know, I was thinking of using RoboFlow dataset. That's why I added this, which is basically get pass, import get pass. And when you do this, it comes up with a box saying that, hey, enter your token here. This is where I was expecting to put my API key. And so it hides from you guys. That's the whole point here for these two lines. And then this part of the code, this is my library. I mean, I have an account on RoboFlow, or I created it, called Python for Microscopists. And within that, I have a project called 3D EM Platelet. And there I have multiple versions of that dataset, because in one version, I had like only, I think, 2 classes labeled. In the other version, I had multiple classes labeled and blah, blah, blah. So I want version number 2, and this is the download. So this should be downloading your dataset. Of course, I'm not doing that because I have already, let's go to the drive, connected my drive to Colab. Go to my drive, Colab notebooks, data, 3D EM platelet, and here I have my YOLO V8 data, and here I have my train folder, valid folder. Exactly the same structure that you see on my desktop folders, and I just uploaded them here, including the data.yaml. That's it. Okay. So I have those, and that's what I'm going to import later on. So first thing first, the YAML file contains all the information in terms of where my training data is and validation data is. So let's go ahead and have a quick look at it. So there you go. My names of the 4 classes here are alpha, cells, mito, and vessels. How many classes do I have? Number of classes, 4. And where is my test images? I don't have test images now, so I just left it whatever. And train is in content drive, my drive, collabs, and blah, 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 all the way train and images, right? So you saw that. My content is all the way down here, and train and images. This is where my images are. And by the way, you have to copy that path into your YAML file. You can edit YAML file using any notepad text. That's just a text file. So I edited that, and this is the information. This is literally all the information that's contained in the YAML file. It's just a YAML extension. Okay. Now, define the number of classes based on YAML, because my YAML has NC4 right there, right? So I say, hey, go ahead, load the YAML file, look at this NC, whatever that number is, that's my number of classes. So instead of manually defining, this is a much better way, right? I mean, you can use a different YAML file and not worry about changing stuff. That's it. We are all set to train the model. So I'm training. I think I trained the model yesterday when I was testing this code. So under results, I should have 200 epochs. You see how I trained it 3 different times, and it created 3 different directories right there. So the more number of times you train, the more, obviously the number it's going to attach to it. I thought of mentioning one other thing. I think that should do actually. And let's go ahead and I'm defining my project right here. This is the destination directory where all of these results are going to be stored. And now this name 200 epochs is a subdirectory within that directory where it stores all the trained data. So let's go ahead and run this. So there you go. And I mean, I defined this. Obviously, I'm not training it yet. And this is where we are training it. And we are capturing the result into a parameter called results, or a variable called results right there. And how do we train? What parameters goes into this model.train? Obviously, you need to give where the data is, and data.yaml tells where the data is. And what is the project name? The project is going to be, or project path, it's going to be right there. And the name of the project is 200 epochs, because I'm going to train it for 200 epochs. And I set a patience of 0 because I want to disable the early stopping. If you put patience of 10 or 20, it looks at the best model. And even if you get the best model, it goes like 20 epochs just to make sure that that is the best, and then it stops, right? So I put 0 because I want to do full 200 epochs in this case. And the batch size, I defined it as 4, and my image size is 800 by 800. So I just defined image size as 800, and let's go ahead and start this. I forgot how long it takes. I was testing multiple models. So let's see. It gives us an idea of how long it's going to take, and I'll pause the video once this thing starts and then continue as soon as this 200 epochs are done. Hopefully not a few hours, but I'm hoping it's a few minutes, but let's see. Okay, so it's looking at the train, it's looking at the cache created and albumentations. It's actually using the data augmentation provided by albumentations library, looking at the validation data set. And now the Adam optimizer is what it's using. My image size is 800, validation size is 800, and epoch 1 out of 200. And let's see how long it actually takes. So it's still doing epoch 100. Now it's doing epoch 200. So it's taking a few seconds, like so 200 epochs should be done. So I thought of actually stopping and showing you results with a with a run that I have done earlier, but it's not fun. Let's actually look at the results from this specific run. So I am going to, let's see if it actually created before stopping. Let's see if it actually created. Yeah, there you go. It created another directory right there called 200 epochs 4, and this is where our results are going to be stored. So I'll return in a few minutes, and let's continue the tutorial. Okay, I'm back. Looks like our 200 epochs are done. There you go. That's 200 out of 200. And what do we look for? So yeah, you can look at the MAP values if I can find them. Like, yeah, they are 50 and 50 to 95. It's like 63%, 72, 87. Mitochondria, we don't have many mitochondria, like I said, so you're not gonna get good accuracy right there. And vessels, that's not bad. So overall, this is pretty good given that we just trained it for 200 epochs. And yeah, so let's go down and see what can we do with this, right? So first of all, this is all numbers, but let's actually visually look at how the training went. So you can load the TensorBoard. Of course, if you're working offline or working on your local IDE, you hopefully know how to fire up the TensorBoard to look at various aspects. Oh God, even in the last video, I got something very similar, but when I do my training, it actually works fine. So maybe I have to change some settings here. Logs, save in the folder runs. Let me quickly try to troubleshoot this. Otherwise, I don't know what's going on here. So unless it's actually looking for these runs somewhere else, maybe it's a path problem right here. But let me just do this one. Test results. YOLO V8. I don't want to waste your time. There is another way of actually looking at this results. I mean, we have the data, we can look at the results, but I mean, it would be cool to actually have a quick look at, okay, these are the weights, 2 weights that it stores the best weight, it stores the last one, and there are a bunch of images right there. So you can actually look at these images instead of looking at the TensorBoard. So let's look at one of these images. So what do we have? Epochs 4 weights, and let's look at results.png. So it should be results epochs dash 4, right? So this is the fourth training, and there is the results.png. So let's go ahead and plot. I'm sorry guys, I don't know why this TensorFlow, there's some silly mistake I'm pretty sure I'm doing here. Probably not looking at the right location is the key, but it worked. Literally it worked yesterday. So anyway, let's look at this. Yeah, so this is not bad. In fact, let me close this side so you can see the result. It's still getting better, but it's not bad. It's converging down here. So there are multiple losses, as you can see. Segmentation loss, that's the box loss. So how, where the box is, right? So do I have the boxes? If so, where are they? So this is the segmentation loss and so on. Classification loss is right here. So how to classify? That's the easy one. Classification is the easy problem. Where it is, like segmentation in the box, is the tough problem. So you can see like the precision was going up, but all of a sudden it went the wrong direction, but then it just came back. So you can, I mean, there's a lot to learn through this. So I'll let you study that. And the other one is epochs 200 epochs 4. Let's actually look at the last batch. What am I looking for? Let's look at train batch 572. Train batch 572. Yeah, that's there. So let's go ahead and plot this one, but instead of third training, we are looking at the training right now. Okay, so it's just basically saving one of those validation images, and now you can actually see how it's doing the detection, and it is doing a pretty good job. You can see how all the cells are correctly detected and all the organelles are correctly detected. So the point here is, if TensorFlow doesn't work, no problem. Go ahead and look at any of these results that it actually stores. You can look at the validation labels, train images. Sorry, I said validation earlier. This is the training image that got segmented. Of course, it's going to do good on the training image. Now let's go ahead and run the inference. First of all, let's change this to 4 again. I was obviously planning on using my previous training, so I'm changing everything here. So let's look at what training, trained weights we have here. So we have the best one, we have the last one. It's up to you what you want to pick. My last one also seems to be okay, right? I mean, from these curves, especially, it was horrible right here, but it came back to the same level where this was heading to. So I'm okay with the last one. Sometimes if it goes crappy right here, you pick the best one. So I'm picking the last one, or you can test both. So there you go. Oh, sorry, not that. I just checked this, but I'm loading the 3. Let's go ahead and change this to 4 and load the weights from 4. Okay, now that it's loaded, let's go ahead and load a test image. And this is my test image. And this is an image that the training never saw. Yeah, this is just a random test image. And I am going to set a confidence of 0.3. We'll have to adjust it based on how the results look like. So let's go ahead and look at the results. Okay, it tells me that there are 30 alphas, 22 cells, 1 mitochondria, 72 vessels, and it took 14 milliseconds to segment. This is why it's amazing. Once you train it, put it on a real-time camera and then let it do the job. You know, this is super fast. That was like incredibly fast. I'm super impressed with this. That's one of the advantages of YOLO. Okay, now that we have the new results, you know that new results can take input as a list of images right there, but I only gave 1. So I'm looking at the 0th right there. Go ahead and plot, and let's look at the results. Plot the results. Humongous image right there because I zoomed into this, but you see how it can be better right here. So probably you can go back and change let's change this to 0.2 and see how that helps or hurts. So there you go. There you go. And now let's look at this. So it did not fill in actually 0.2. The problem is if you have multi-classes like this and you start adjusting the threshold for all the classes, then sometimes you get over a lot more classes in certain objects and a lot few classes. So again, adjust the threshold to see how that works for you. But let's go down and check a couple of things. So extracting the bounding boxes, how do you extract the bounding boxes? So if you look at the first or result number 0, which is the result for this specific image, you can see that, okay, the keys are boxes and masks. So within this new result, you have 2 things, the boxes and the masks. And the names of these classes are alpha, cells, mito, and vessels, and these are the numbers associated with that, like 0 to 1 is alpha, and here is the original image. Okay, and you can go into the boxes and the masks, and you can extract only the boxes or the masks. Again, this is instant segmentation, so you have both boxes and masks. Okay, so with that information, what can we do? Let's go ahead and extract masks. Okay, so you can extract the bounding polygons. These are all the polygons for this mask. So masks.xyn, that gives you all the polygons. Now if you go down, do I have the example? Yeah, masks.data gives you the data about the masks. So go ahead and look at so we have 144 objects detected in this specific image, and it gives you the data for each and every one of these masks. So let's push the mask to our CPU, because all of this is in GPU right now. Let's push it to CPU so we can play with it. You can extract some numbers. So let's go ahead and push this to CPU, and I'm converting that into a NumPy array. So if I show the image, now this is just a NumPy array. Now show me the 0th object. That's where the 0th object is. Now show me, I don't know, let's just do 1 right here. You'll see object number 1 right there. You got the point. I don't know, show me 10th object. Let's just do that. And that object is not this is something I have to look into. If you train more, again, you get this continuity and everything, but this is a result of limited training. And this is one thing that I realized between Detectron and YOLO. YOLO is fast, but I feel like there's a compromise in accuracy, or it is a bit more hungry when it comes to data. So you need to train a lot more epochs with a lot more data to get the same level of accuracy. So again, it's a compromise between this accuracy and speed. Again, I'll let you, in some cases this is okay, but in some instances, for example like this, if I want to segment the cells, I need to find a way to further train or optimize this. Okay, so what class names do I have? Alpha, cells, mito, vessels. So I'm going to extract the bounding boxes that contain these class IDs. And for each of these classes masks, go ahead and print out. So what am I trying to do, figure out here? Obviously, how many alphas do I have? How many mitos do I have in this image? So I have 34 alphas. So I'm just showing you, after you're done segmenting, certain steps to extract your data so you can go ahead and do other stuff. So not just detect and say done. The stuff you get from watching my videos, guys. Okay, now extracting masks for a specific class. Now I'm like, okay, just show me the masks for alphas and cells. Of course, you're extracting those masks, and now get the original image. Our original image is 800 by 800 by 3, right? So I mean, this is a grayscale image in this case. Sorry, a grayscale image converted to like RGB image in this case, and now display the original image so you can see exactly how my original image is with an object on top of it, right here. Yeah, so you can play with that, but now let's go ahead and calculate the region properties for all the objects. So all I'm doing is iterating through each object, getting these objects right here, and then using the scikit image measure.region probs to actually extract the region props for all of these and capturing them into a CSV file. So when I actually download the CSV file, you should be able to see, actually, let's look at the data frame right here. And the data frame you see for class name is alpha, and the area and the perimeter. So these are the 3 I captured, and now you have a CSV file that you can play with. Now you can download and work with Excel and all that kind of stuff, but we love Python, right? So let's use Seaborn, and let's use the area information and do a swarm plot. So now I want to visualize how the area is. Obviously the cells, they have much larger area, they are pretty big, so you can see all those real cells. These are all probably the misidentification because our threshold is set to 0.2 actually right now. If we change it to 0.4 or something, only the large ones will be identified, all the little ones will be gone. So we have only one mitochondria right there. Most of the vessels, they have uniform spread. You can also do box plot if you're not a swarm plot type of person. So that's the spread is pretty tight for all of these other ones. For the cells, it's pretty much a spread. Okay, all of that is fine. Now let's say, okay, this is great. I want to deploy this in real time, for real time applications. You can export this as ONNX format. And I've done a couple of videos on ONNX in the past, but ONNX is a lightweight, let's say, model that can be deployed pretty easily. So go ahead and download this and create a web app or something. Okay, that's a relatively long video, but I hope you learned something here. It's a full project, as you can see, all the way from images to annotations, converting annotations to your into your YOLO format, and then training a model, and then segmenting your future images, and extracting object parameters here. And again, the accuracy wise, again, it's not a real project. I cannot just go submit and say, hey, give me my master's. Well, I have a PhD, but I'm saying you cannot just go and say that, because the results are not great. This is where I leave it to you. Go annotate more images, get more images, and train for 500 epochs and see how the results actually change, and compare these results with Detectron 2 and see what the merits of Detectron 2 is and what the merits of YOLO is compared to each other, and what the drawbacks of each of these are, so you understand what tool you would like to use for what type of specific job. I'll do that exercise if I have time, but I want to get this out right away to you guys so you can learn all about YOLO. I hope this video really helped you. And again, thanks for your patience for watching all the way to the end. And do not forget to hit the subscribe button. Thank you.